Hi everyone, my name is Yedo. I'm a senior in the class of 2025, and today I'll be going over continuity, differentiability, and the three theorems, which are extreme value theorem, intermediate value theorem, and mean value theorem. So let's start out with the definition of continuity. So a function that is continuous is a function that doesn't have sudden changes in value. So a way to think about this would be a continuous function can be drawn without lifting the pen off the paper or the board or whatever it might be. So this visual right here. So this function would be a continuous function. I can draw it without lifting the pen. So, okay. And this will mean that a continuous function cannot have any holes, jumps, or asymptotes. So over here, these are examples of discontinuity. So first, starting with function f, it has a hole at 0.12. As you can see, the function is defined on all the x values except for at 1. So that would be a hole. And then function g, this is what you would see in a piecewise function. So the function comes up and it just stops, and then it jumps and then continues going. And this again can't be drawn without lifting the pen, so that would be another discontinuity. And then finally we have function h, which has an asymptote as it approaches x equals 2. From the left it goes infinitely high, and it goes infinitely low as it approaches from the right. So that is an asymptote or an infinite discontinuity. Okay, so as you can see, a hole is classified as a removable discontinuity, and jumps and asymptotes are classified as non-removable. So the difference between the two is that a removable discontinuity has the limit exists at that point that has the discontinuity. So as you can see here, the limit as x approaches 1 from the left and from the right are equal at 2. So the limit exists. The limit as x approaches 1 exists. But if we move over to g and h, both of these we can see that as limit, the limit as x approaches 1 from the left and the right are not the same. As from the left it would be 2, from the right it would be negative 2. So the overall limit doesn't exist. And here, as x approaches 2 from the left and from the right, the limits are respectively are positive infinity and negative infinity, which is not equal. Again, the overall limit does not exist. So leading on from the definition of continuity, the first theorem that we're going to get into is the extreme value theorem. So the extreme value theorem states that on a function that is continuous on a closed interval from a to b, we'll have an absolute maximum and minimum value within that interval or that domain. So I have an example right here. So this function f of x is continuous on the closed interval from negative 3 to 3. So as you can see, from negative 3 all the way up to 3, it is continuous. You can draw it without lifting the pen. And as you can see, the absolute minimum value right here, absolute maximum. So that is the pretty basic definition of the actual theorem, but the way that you can implement this is in finding, if you're given, let's say, a quadratic or any sort of function and you're told to find the absolute maximum and minimum points, you can use this theorem to do that. So how you can do this is, for whatever function, as the extreme value theorem states, you know that there will be a maximum value and a minimum value at some point. So, including the endpoints, which in this case are negative 3 and 3, and some points in between. In this case, you can see it could be here, or maybe right here. So, it's not possible for a maximum or a minimum value to be at any point that either isn't an endpoint or has a slope that isn't 0. So what I mean by that is, let's say for a second, we know that this is an absolute minimum value, right? But this point right here, let's say, that can't be an absolute minimum because that's got a slope that's kind of like that. But point right here, that slope is going to be 0. So where I'm trying to go with this is by finding critical points, which are points where the slope or the derivative of the equation is 0, or endpoints for both of the directions. So on any given function, the absolute maximum or minimum value is going to be either on a critical point or an endpoint. So what you can do with this is you can solve for an equation. For example, on a quadratic, you would solve for x equals 0, or y. What value of x results in y being 0, right? And then you would use the endpoints and those critical points that you just found. You plug them into the equation, and whatever y value you end up getting that is highest, that would be the absolute maximum, and whatever y value that ends up being the lowest would be the minimum. Yeah. All right, so the next theorem that is based on the idea of continuity is the intermediate value theorem. So the intermediate value theorem states that on a continuous function on the closed interval a and b, there exists an x value, c, such that f of c will give you any L value or any Y value that is between f of A and f of B. So that is complicated, but I'll simplify it. So you can see that A right here, B right here. If you pick any value of any Y value between f of A and f of B, we'll put the dot right about Y equals, let's say, 7, and if we put a dotted line there, wherever we move that dotted line, that is between f of A and f of B, which are these two dots, there is a point on the graph that crosses that dotted line. So that is what this theorem is pretty much talking about. So if we, again, are looking for 7, some value f of c equals 7. So some value f of c will equal 7, where c is some value between a and b. So yeah, hope that makes sense. All right, so the next concept we're going to look at is the concept of differentiability. So differentiability is defined, okay, a function that is differentiable will first of all be continuous. So a function that isn't continuous cannot be differentiable. It's kind of like rectangle square type deal. And beyond just being continuous, a function that is differentiable must have a derivative that exists at every point. So a derivative for every x value on that function must exist, meaning it can't equal infinity, whatever. So we'll look at that right now. So this is an example of a function within this domain that is differentiable because, as you can see, it is continuous. There are no poles, jumps, asymptotes, or whatever it might be. And also, on every point, the derivative is going to equal a value that is not infinity. So if you go right here at the tip, it would maybe equal like 20, something like that. Down here, it equal negative 20-ish. Up here, it'd be 0. But at no point does the derivative not exist. And then as we move on to this function right here, this is what you would see in absolute value function. This is an example of a function that is not differentiable because as you come in, what you see is the limit of the derivative from either side is not equal to each other. So this would be a function that is not differentiable. So this would be called a cousin. It kind of looks like the tip of a roof or an angle. It's not gradual. It's not like a round tip, but it's a very sharp tip. So that's called a cousin. That is a function with a cousin is non-differentiable. Okay. And then another example here. As you can see, you have a vertical asymptote as you come in like this. At that point, right in the middle, the instantaneous rate of change or the derivative would equal infinity. So that would also be a function that is not differentiable because the derivative at that point does not exist. Okay? Okay, now that we've learned about the concept of differentiability, the next theorem that is based on the concept of differentiability is the mean value theorem, or MVT. So this theorem states that on a function that is continuous on a closed interval and differentiable on the open interval AB, the average rate of change from A to B, which is represented by this expression, is equal to the instantaneous rate of change, or the derivative, at any point C that is greater than or equal to A and lesser than or equal to B. So pretty much on the interval A to B. So to visualize, if we have a function that is differentiable on the open interval A to B and continuous on the closed interval, which this is a parabola but on a certain domain, the average rate of change from A to B, which let's say for now is 2, at any point between the x values of A and B, you will find, or not at any point, at some point between A and B, so at some point on this graph, the slope, the tangent line to this graph will equal the slope between A and B. So coming back to here, what this represents, f of b minus f of a will give you the difference in y value, and then b minus a will give you the difference in x value, and then putting this in a fraction will effectively give you the slope, and f prime of c, c being some point between a and b, will give you again the slope. And then what this pretty much is saying is, if you're at some point between a and b, so pretty much at some point on this partial parabola, there is a point on which the slope of that point, or the instantaneous rate of change at that point, will equal the average rate of change between